Okay, we're going to take a quick survey here, a quick little look at the idea of light and how it relates to electrons and the light that it's emitted when electrons change energy levels. And so what we're going to start with is just a basic overview of the definition, a couple of definitions that will be very useful to you. The first one has to do with this definition of wavelength. Wavelength is abbreviated with the Greek letter lambda that looks something like this. So anytime you're looking for the wavelength in a problem, you're probably going to find it associated with that particular symbol. And so you see that symbol right here. And in this particular example, we've shown a wave that goes from here to here. The definition of wavelength is the distance between similar parts of adjacent waves. So, we could talk about measuring from the trough to the trough, and it would be that same wavelength that you see up above. So that is wavelength. And wavelength can be measured in nanometers or meters or whatever other unit of length you might normally use in the SI system. You'll just want to watch your units carefully to make sure you're working with the right unit. The other important property of a wave that we're going to consider is the frequency. And frequency is represented by this, which I believe is the Greek letter nu. And that is how we represent frequency. Now, frequency is how often the wave goes down and up and down and up and down and up and down and up. That was 4 wavelengths it shows here. The frequency is how many times it does that in a second. So the frequency here is 4 cycles per second. We would call that 4 1/seconds. That's cycles per second. Or 4 seconds to the -1, or 4 hertz. And hertz, H-E-R-T-Z, is abbreviated Hz. So you may find this unit in things like megahertz or kilohertz or some other SI unit. And so you've just got to be careful with your units with these. So in chemistry, this section of chemistry and physics, we're especially interested in electromagnetic waves. And electromagnetic waves include a lot of waves that we use on a regular basis. Radio that we use for communication or for listening to as we're driving along in our car, for microwaves that we use for communication or that you use to maybe warm up some food or pop some popcorn, infrared radiation that we may use as a food warmer, a light that puts energy down onto some food and warms it up, or we may use it in our remote control devices. Our remote control, many of them, most of them, like for your TV or your video camera or your stereo, use infrared radiation to carry the signal from the handpiece to the device. And of course, visible light, ultraviolet light that goes from the high end, purple, like black light, is almost up at the ultraviolet end. And then ultraviolet includes also things like we use to sterilize goggles in our goggle cabinet. So the sun puts out a lot of UV light, and it is that UV light that has enough energy to cause some damage to our skin and cause skin cancer and things like that. And then as we continue on the electromagnetic spectrum, we have things like X-rays and gamma rays. So one thing that's important to us for all of these wavelengths is that they all travel at the same speed, the speed of light. And we represent the speed of light with a C, and depending on how many sig figs you want to use, the standard for our purposes is just going to be 3.0 times 10 to the 8 meters every second. That's the speed of light. So in our calculations, that's what we will use for c. And you'll also notice here is a relationship kind of between wavelength and frequency. And so we're going to learn to do this calculation so that we can go from wavelength to frequency in our calculations. So, what is the equation that shows the relationship between wavelength and frequency? Well, the speed of any wave, and we're going to focus just on electromagnetic waves. So the speed of any wave, there's the speed of light, that's how fast electromagnetic waves travel. The speed of any wave is equal to the wavelength times the frequency. So in this relationship, if we know any two of those three things, we can calculate the other. Well, that means if we know the speed of light, we can easily know one of them, and if we know the other, we can calculate the third. That's the equation that we've been using. So if we have a laser that puts out light that's say 670 nanometers is the wavelength, we might be especially interested in finding out what is the frequency. Now remember, frequency is abbreviated with this funny Greek letter nu. So the relationship we're going to use is C equals lambda times nu. So if we rearrange that, we know that we can divide the speed of light by the wavelength, and we will get the frequency. So we have to be a little bit careful here, however, because the speed of light is expressed in meters per second, 3 times 10 to the 8 meters per second, and the wavelength was 670 nanometers. And now those units will not cancel out, so we have to convert one of them to the other, and what we're going to choose to do is convert this one. So how many nanometers are in 1 meter? Because we're going to convert 2 meters. Well, I like to use one big thing is a lot of little things, and nano means 1 millionth, so there are 10 to the 9, or 1 million nanometers in 1 meter. And so we're going to do this conversion before we do the division. So that calculates to 4.78 times 10 to the 14 as the frequency. So wavelengths of light oscillate at an extremely rapid frequency. Now, what are the units that are left here? You will notice that the meter here is upstairs. The meter here downstairs is on top of our fraction. So those factor out, and our unit is seconds to the -1, or you might call that hertz. So that's how we can calculate the frequency of any wavelength of light if we know the wavelength of light. Now, what is the equation that shows us how to get the amount of energy? What you will notice here is that with this electromagnetic spectrum, we have some kinds of energy, some little packets of waves of light. Here I am stumbling around because sometimes we think of light as a wave and sometimes as a particle, and we're really going to call little packets of light photons. And a single photon of visible light has enough energy to activate the retinol in the and other chemicals in the retina of your eye so that you detect light. Light that's down on this end of the spectrum, or other kinds of electromagnetic energy, do not have enough energy to activate your eyes. And up here on this end of the spectrum, we don't see those things. The chemical reactions don't occur. And also, if we're looking at those things, we may get enough energy to do damage to our eye, because up here we have a greater amount of energy involved with these wavelengths of light. So we are also going to be especially interested in calculating the amount of energy associated with these different wavelengths of light. So what's the equation for showing the relationship between wavelength and energy? Well, the equation is this. Energy is equal to the frequency of the light times a constant. Well, in other words, the greater the energy, the greater the frequency, the greater the energy of the light will be, and there's a constant then that helps us do this conversion. The constant is known as Planck's constant, and Planck's constant is this value of h, and it's on your AP equation sheet, so don't worry that you have to memorize it, but it's 6.626 times 10 to the negative 34, one of the smallest numbers you'll regularly use in chemistry class. 6.626 times 10 to the negative 4 joules times seconds. So if you have a stream of these photons, joules times seconds, it helps you calculate how much energy they are producing. So